In this second class of Chapter 2 of the course of Plane Geometry, several postulates about the planes are presented. The following topics will be shown: postulate of Euclid, plane definitions, division of a line segment, proportionality between of line segments. In this first slide of this second class of Chapter 2 of this course, it is presented in Figure 212 the Euclid's postulate for non-parallel lines. This postulate states that if a line S in a plane intersects two other lines R and T that also belong to the same plane, and the sum of the internal angles formed in one of the half planes defined by line S is less than 180 degrees, then the two lines R and T intercepted by line S will intersect one another at that point of the same plane. Figure 212 on the slide shows two lines T and R, and the line S that intercepts the two lines T and R. The same plane analyzed is the alpha half plane. In the second part of this slide is presented the Euclid's postulate of parallel lines. This postulate states that at a point in a plane passes only a single line parallel to another line that belongs to the same plane. In this second slide of this second class of Chapter 2 of this course is presented a theorem about the definition of a plane by a straight line and a point. The theorem, in his statement, states that by a straight line and a point that does not belong to this line passes a single plane. The proof is performed according to Figure 213, where a line S with the 2 points B and C belonging to the straight line S, and a point A that does not belong to said line S are presented. The 3 points marked A, B, and C are not collinear. That is, they are not on a single line, because the point A does not belong to a straight line S. So you have the situation determined by the postulate I had presented in the previous lesson, that says that by 3 distinct and non-collinear points pass only a single plane. That is, 3 different points in space and none in a straight line, that is, not collinear, determine a single plane. This slide presents a theorem on the definition of a plane by 2 concurrent lines. The statement of the theorem states that if there are 2 distinct and concurrent lines, that is, the 2 lines have a common point at the intersection of these lines, there is a single plane containing these 2 lines. The proof of the theorem is presented in Figure 214 of the slide, where 2 lines S and T are shown, and the point A is marked on line S and point B on line T. The point K is also marked at the intersection of the lines S and T. Since points A, B, and K are distinct and they are not aligned, that is, they are not in the same straight line, since points A and B are located on different lines, then you have 3 distinct and non-aligned points. So again, postulates already present in the previous lessons that says that for 3 different and non-collinear points passes a single plane, and that realizes the proof. Thus, this theorem states that by 2 concurrent lines in space passes a single plane. In this slide, it presents a theorem whose statement says that 2 parallel lines determine a single plane. The proof is shown in Figure 2.15, presented on the slide, where 2 parallel lines S and T are presented, which are intercepted by the line key A. Also marked on line S is a point B different from point K. The definition of parallel lines asserts that they are not concurrent and that the distance between 2 points of intersection, each point in one of the lines, belongs to a perpendicular line that crosses the 2 lines, is constant for all the transverse lines that have the same terms. These lines must belong to the same plane. So, drawing a perpendicular to one of the line, this will determine 2 points of intersection. And marking another point in one of the line, there will be 3 different and non-aligned points, K, A, and B. Those points are not collinear points. This situation returns to the postulate already presented in the previous lesson. That postulate states that by 3 different and non-collinear points passes only a single plane. This proof is valid for any perpendicular to 2 parallel lines and a different additional point in one of these parallel lines. In this slide is shown a method for dividing a line segment into n subsegments of equal dimensions. The slide in figure 2.16 shows the method. To subdivide a line segment AB into n equal subsegments, first the line segment AB with dimension specified for this segment is drawn. Next, auxiliary line segment AP is drawn, using any acute angle S with the original segment AB. In the auxiliary line segment AP are marked N subsegments of any size, but all with the same chosen dimension. Continuing with the process, a line segment is drawn which join the last marked point to point B. Then, parallel lines are drawn through each of the points defined by the subsegments marked in the line segment AP. The points of intersection of this parallel line in the original line segment AB define the subsegments of the original segment AB. This marks the points M, N, O, P, Q, R in the original segment AB. In this last slide of the second class of Chapter 2 of the Basic Geometry course shows the proportionality between line segments. Figure 2.17 shows on the slide presents 2 non-parallel lines, AI and BJ, intersected by 5 parallel lines, AB, CD, EF, JH, IJ. The line subsegments generated in the non-parallel lines AI and BJ result in a proportionality between these subsegments according as shown in the figure, or the value of the division of the dimension of the subsegments AC by the dimension of the subsegment BD is equal to the division of the dimension of the subsegment CE by the dimension of the subsegment GF, and so on. This division always has the same constant value. Thus, this demonstrates proportionality allows the calculation of the dimension of a subsegment when the value of the dimension of another subsegment is known.